Welcome back to Whispering Universes, where we trace the stories written in starlight and explore the vast architectures that populate the cosmic dark. Tonight, we turn our attention to something you can see with your own eyes on a clear autumn evening, something that has watched over human civilization since before we had words to describe it. Look up into the constellation Andromeda, away from city lights, and you might notice a faint, fuzzy patch of light. Your eye is capturing photons that have traveled for 2.5 million years across intergalactic space, light that left its source when our ancestors were just beginning to shape stone tools on the African savanna. You are looking at another galaxy, a cosmic island of hundreds of billions of stars, and it is coming toward us. The Andromeda Galaxy, catalogued as Messier 31 or simply M31, is our closest large galactic neighbor, a spiral galaxy that mirrors our own Milky Way in many ways, yet remains profoundly different in others. It hangs in our night sky like a promise and a warning, a reminder that our cosmic neighborhood is far more dynamic than the stable heavens ancient peoples imagined. Tonight, we will explore this remarkable object from every angle we can imagine: its structure and composition, its history and evolution, the stellar populations that inhabit it, and the inevitable future that binds it to our own galaxy in a gravitational dance that has already begun. What makes Andromeda so compelling is not just its proximity or its beauty, though both are considerable. It is the way this galaxy serves as a mirror for our own, a laboratory where we can observe processes that are difficult or impossible to study in the Milky Way from our position embedded within it. When we look at Andromeda, we see what an observer in another galaxy might see when they point their telescopes toward us. We can map its spiral arms, study its stellar populations, observe its satellite galaxies, and track its movements through space with a clarity that our own galaxy denies us. Every discovery we make about Andromeda teaches us something about the Milky Way, and every question we ask about our home galaxy finds a parallel in our studies of our neighbor. But Andromeda is also a dynamic actor in our cosmic story. The galaxy is not standing still in the void. It is falling toward us, pulled by the mutual gravity that binds the local group of galaxies together. In approximately 4.5 billion years, Andromeda and the Milky Way will collide, not in a violent impact that destroys stars, but in a long, complex merger that will reshape both galaxies into something new. This future collision has already influenced our present, creating tidal streams and altering orbits, a gravitational conversation that spans the intergalactic gulf. Here on Whispering Universes, we often explore the most extreme and exotic phenomena the cosmos has to offer, but tonight we focus on something closer to home, something familiar yet strange. Andromeda represents the scale of structure that dominates the modern universe, the galactic scale where gravity has woven billions of stars into coherent systems that live and evolve over billions of years. Understanding this one galaxy means understanding how galaxies in general function, how they form and grow, how they interact with their environments, and how they ultimately determine the fate of the matter and energy contained within them. As you settle into this exploration, imagine standing on a planet orbiting a star in Andromeda, looking back across the void toward the Milky Way. From that perspective, our galaxy would appear much as Andromeda appears to us, a spiral of light against the dark, spinning slowly over eons, harboring its own mysteries and stories. The symmetry is profound. We are observers and observed, neighbors separated by millions of light years, yet bound by the same fundamental physics, the same gravitational destiny. Tonight, we will journey through the structure of Andromeda, examining its spiral arms and stellar disk, its bulging core and extended halo. We will discuss the populations of stars that make up this galaxy, from ancient red giants that remember the galaxy's youth to brilliant blue stars that have formed only recently. We will explore the satellite galaxies that orbit Andromeda, small systems caught in its gravitational embrace, and we will consider the supermassive black hole that lurks at its center, an invisible anchor around which hundreds of billions of stars revolve. We will trace the history of our observations of this galaxy, from ancient naked-eye sightings to modern multi-wavelength surveys, and we will project forward into the future, imagining the collision that awaits and the merged galaxy that will eventually emerge. Let us begin our exploration of this quiet neighbor in the dark, this island of stars that has accompanied our galaxy since the universe was young, this future partner in the greatest gravitational dance the local group will ever witness. The story of Andromeda is our story too, written in the language of gravity and light, played out over timescales that dwarf human history, but which we can nevertheless observe and understand. The human relationship with Andromeda begins long before astronomy became a science, long before telescopes revealed the true nature of the fuzzy patch visible in the autumn sky. Ancient Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 inches, his Book of Fixed Stars, calling it a small cloud, one of the first recorded observations of what we now know to be a galaxy beyond our own. He could not have known what he was seeing, could not have imagined that this small cloud contained hundreds of billions of stars, or that it lay millions of light years from Earth. To him and to observers for nearly another 1,000 years, it was simply a curious feature of the night sky, noteworthy for its faint glow and nebulous appearance. When Charles Messier compiled his famous catalogue of deep sky objects in 1764, he included this nebulous patch as the 31st entry, M31, though he too had no idea what it truly represented. Messier was a comet hunter, and his catalogue was essentially a list of things that might be confused with comets, but which were fixed in position relative to the stars. The Andromeda Nebula, as it was then called, earned its place in this catalogue as a particularly prominent example of the fuzzy, comet-like objects that populated the sky but never moved. It would take more than 150 years before astronomers understood that they were looking at an entirely separate galaxy, a realization that would revolutionize our understanding of the cosmos. The breakthrough came in the 1920s when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to resolve individual stars within the Andromeda Nebula. Among these stars, he identified Cepheid variables, stars whose brightness pulsates in a regular pattern related to their absolute luminosity. Henrietta Swan Leavitt had earlier discovered this relationship, providing astronomers with a cosmic distance ladder. By measuring the period of these Cepheid variables in Andromeda and comparing their apparent brightness to their calculated absolute brightness, Hubble determined that the Andromeda Nebula must be approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. This was the great debate settled by observation. Andromeda was not a nebula within our galaxy, but an island universe in its own right, what we now call a galaxy. Hubble's measurement was actually an underestimate due to confusion between different types of Cepheid variables, a mistake that was later corrected when Walter Baades' work in the 1950s refined our understanding of stellar populations and distance measurements. The modern value for Andromeda's distance is approximately 2.5 million light-years, nearly 3 times Hubble's original estimate, but the fundamental discovery remained valid. We live in a universe populated by galaxies, each containing billions or hundreds of billions of stars, separated by vast reaches of mostly empty space. This realization transformed astronomy and philosophy in equal measure. The universe was suddenly far larger than anyone had imagined, and the Milky Way, which had seemed to encompass all of existence, became just one galaxy among billions. Our position in the cosmos shifted from central to peripheral, a continuation of the Copernican revolution that had removed Earth from the center of the solar system. Now, the solar system itself, and even the galaxy containing it, were revealed to be unremarkable components of a much grander structure. Throughout the 20th century, as telescope technology improved and our understanding of physics deepened, Andromeda became one of the most studied objects in the night sky. Radio telescopes revealed neutral hydrogen gas distributed throughout the galaxy. Infrared observations penetrated dust clouds to reveal star-forming regions. X-ray telescopes detected high-energy sources, including X-ray binaries and the supermassive black hole at the galactic center. Each wavelength of light provided new information, building a comprehensive picture of this complex system. Modern surveys have mapped Andromeda in exquisite detail, resolving individual stars even in its dense central regions, tracing the motions of stellar populations, mapping the distribution of dark matter through gravitational effects, and identifying thousands of globular clusters orbiting in its halo. We can now study Andromeda with a precision that would have seemed magical to early observers, measuring the velocities of stars, determining their chemical compositions, estimating their ages, and reconstructing the galaxy's history from the fossil record preserved in its stellar populations. As you drift deeper into this exploration, consider the profound shift that Andromeda represents in our cosmic understanding. What seemed to be a small, fuzzy patch to naked eye observers revealed itself to be a galaxy as grand as our own, populated by stars and planets, containing its own history of formation and evolution, and embarked on a future that will eventually intertwine with ours. The discovery of Andromeda's true nature ranks among the most important in astronomical history, a moment when the universe expanded beyond our wildest imaginations. When you look at Andromeda through a powerful telescope or in images captured by observatories, you see a structure that immediately suggests rotation and organization. The galaxy presents itself to us tilted at an angle of about 77 degrees from edge-on, allowing us to perceive its spiral structure while also seeing some depth in its disk. This fortuitous geometry makes Andromeda ideal for studying spiral galaxy architecture, neither fully face-on, where disk structure is compressed along our line of sight, nor perfectly edge-on, where the spiral pattern becomes difficult to discern. The spiral pattern itself consists of regions where stars and gas concentrate more densely than in the surrounding disk, creating the luminous arms that wind outward from the central bulge. These arms are not permanent structures made of specific stars. Rather, they are density waves, regions where the gravitational potential creates traffic jams of stars and gas that move through the disk at a different speed than the stars themselves. Individual stars orbit the galactic center on their own paths, but they slow down slightly when they enter a spiral arm region due to the increased gravitational pull, creating the appearance of a persistent structure even though the stars comprising it are constantly changing. Andromeda possesses a multiple-arm spiral structure, though the exact classification has been debated among astronomers. Some features suggest a grand design spiral with two prominent arms, while other observations reveal a more complex pattern with multiple arm segments and spurs. This complexity is typical of large spiral galaxies and likely results from various perturbations, including gravitational interactions with satellite galaxies and inherent instabilities in the galactic disk. The spiral arms are most prominent in the optical and infrared, where young, hot stars and star-forming regions concentrate, but they can also be traced through radio observations of neutral hydrogen and molecular gas. The disk of Andromeda extends to approximately 110,000 light-years from the galactic center in the optical wavelengths, making it significantly larger than the Milky Way's approximately 100,000 light-year disk. However, like our own galaxy, Andromeda possesses an extended disk of older stars and gas that reaches much farther out, detectable through careful surveys that can pick out faint stellar populations against the background sky. These outer regions are dynamically interesting, showing evidence of warps and asymmetries that likely result from past interactions with smaller galaxies. At the heart of the spiral structure lies Andromeda's bulge, a dense concentration of mostly older stars that orbit the galactic center in random directions rather than in the organized rotation of the disk. The bulge appears yellowish in color photographs, reflecting the light of red giant stars and indicating a population that formed early in the galaxy's history. This central region is gravitationally dominant, containing a significant fraction of the galaxy's total stellar mass in a relatively compact volume. The density of stars in the bulge is so high that if our solar system were located there, the night sky would be filled with stars bright enough to cast shadows, and close encounters between stellar systems would be far more common than in our current location in the Milky Way's disk. Surrounding the visible galaxy is the halo, a roughly spherical distribution of old stars, globular clusters, and dark matter that extends far beyond the disk. The stellar halo is faint and difficult to observe because the stars are spread so thinly across such a large volume, but it provides crucial information about the galaxy's formation history. Many halo stars likely originated in smaller galaxies that merged with Andromeda early in its history. Their original galactic structures destroyed, but their stars preserved as fossil evidence of these ancient mergers. The total mass of Andromeda has been estimated through various methods, including measuring the rotation speeds of stars and gas at different distances from the center and observing the motions of satellite galaxies. These measurements consistently indicate that the vast majority of the galaxy's mass is not in stars or gas, but in dark matter, the mysterious substance that interacts only through gravity and whose nature remains one of physics' greatest unsolved problems. The dark matter halo extends well beyond the visible galaxy, creating a gravitational well within which all the visible matter sits. Estimates suggest Andromeda contains approximately 1 trillion solar masses of total mass, significantly more than the Milky Way's estimated 800 billion to 1.5 trillion solar masses. This architecture of spiral arms, bulge, disk, and halo represents the standard structure of large spiral galaxies throughout the universe. By studying Andromeda's structure in detail, we learn about the processes that form and shape these systems, about the interplay between dark matter, gas, and stars, and about the dynamical mechanisms that maintain these beautiful, long-lived patterns. The spiral form is not accidental or arbitrary, but emerges naturally from the physics of rotating, self-gravitating systems, a testament to how gravity sculpts matter into patterns that repeat across cosmic scales. As your mind traces these spiral arms winding through space, consider how each element of this structure has a purpose and a history, how the density waves that create the arms facilitate star formation, how the bulge harbors the galaxy's oldest stellar populations, how the halo preserves evidence of ancient mergers, and how the dark matter provides the gravitational scaffolding that holds it all together. Within Andromeda's vast structure live an estimated 1 trillion stars, perhaps more, each following its own orbit around the galactic center, each at its own stage in the stellar life cycle, each contributing its small part to the total light and gravitational influence of the galaxy. These stars are not uniformly distributed or uniformly aged. Rather, they form distinct populations with different characteristics, different spatial distributions, and different histories. And by studying these populations, we can reconstruct much of Andromeda's evolutionary story. The oldest stars in Andromeda reside primarily in the bulge and halo, populations that likely formed within the first billion years after the Big Bang. These stars are metal-poor, meaning they contain relatively small amounts of elements heavier than hydrogen and helium, because they formed from gas that had not yet been enriched by previous generations of stars. Metal-poor stars tend to be redder and dimmer than younger, metal-rich stars of the same mass, and they dominate the yellowish color of the galactic bulge when viewed in optical light. Many of these ancient stars are red giants, stars that have exhausted the hydrogen in their cores and expanded to enormous sizes while burning hydrogen in shells around their helium cores. The globular clusters that orbit in Andromeda's halo provide particularly clear windows into the galaxy's ancient past. These dense, spherical collections of stars, each containing tens of thousands to millions of stars, bound tightly by gravity, formed early in the galaxy's history and have survived largely intact ever since. Andromeda hosts somewhere between 400 and 500 confirmed globular clusters, significantly more than the Milky Way's approximately 150, and studying their properties provides insights into the conditions that prevailed when the galaxy was young. The chemical compositions of stars in these clusters, their ages estimated through careful comparison with stellar evolution models, and their orbital characteristics all contribute to our understanding of how Andromeda formed and evolved. In contrast to these ancient populations, the disk of Andromeda contains stars of all ages, from ancient red giants similar to those in the bulge to brilliant young blue stars that formed within the last few million years. The youngest stars concentrate along the spiral arms, where dense molecular clouds provide the raw material for star formation. These regions glow brightly in ultraviolet light from hot, massive stars and in infrared light from the dust that surrounds newly forming stars and blocks visible light. When we observe these star-forming regions, we are watching the same processes that formed our own sun some 4.6 billion years ago, processes that continue throughout the galaxy wherever conditions permit. The intermediate-age stellar populations, stars formed between 1 billion and 10 billion years ago, dominate the mass of the disk and provide most of the light we see in optical wavelengths. These stars, similar in many ways to our Sun, follow nearly circular orbits in the galactic plane, contributing to the smooth, organized rotation of the disk. Their chemical compositions reflect the gradual enrichment of the galactic gas over time, as successive generations of stars formed, lived, and died, returning their processed material to the interstellar medium through stellar winds and supernova explosions. Andromeda's stellar populations also include more exotic objects that provide crucial information about stellar evolution and galactic dynamics. Variable stars like Cepheids and RR Lyrae stars pulsate regularly, their periods related to their absolute luminosities, making them invaluable as distance indicators. X-ray binaries, systems where a normal star orbits a neutron star or black hole and transfers material onto it, emit high-energy radiation detectable by X-ray telescopes. Planetary nebulae, the glowing shells of gas ejected by dying sun-like stars, can be identified and counted to estimate star formation histories. White dwarfs, the dense remnants left behind after stars like the Sun exhaust their nuclear fuel and populate the galaxy in large numbers, though their faintness makes them difficult to detect individually. Recent surveys, using powerful telescopes like the Hubble Space Telescope, have resolved individual stars in Andromeda across large portions of the galaxy, creating unprecedented catalogues that contain millions of stars with measured brightnesses, colours, and in some cases, motions. These catalogues allow astronomers to construct colour magnitude diagrams, plots that show how stellar brightness relates to colour and that reveal different stellar populations as distinct features. The main sequence, where hydrogen-burning stars spend most of their lives, appears as a diagonal band, while red giants cluster in a distinct region and white dwarfs occupy another area of the diagram. By analysing these patterns across different regions of Andromeda, researchers can map how stellar populations vary with location and reconstruct the galaxy's star formation history in detail. The chemical composition of stars varies not just with age, but also with location in the galaxy. Stars in the inner disk tend to be more metal-rich than those in the outer disk, reflecting a radial gradient in chemical enrichment that results from star formation being more vigorous and sustained in the inner regions where gas is denser. This gradient provides information about how gas flows through the galaxy, how metals are distributed by stellar winds and supernovae, and how the galaxy has grown over time through accretion of gas from the intergalactic medium and through mergers with smaller galaxies. As you imagine this vast population of stars, each a nuclear furnace, transforming hydrogen into heavier elements, each moving on its own path through space, consider the scale of structure and organization that gravity creates. These trillion suns do not move randomly, but participate in the collective motion of the galaxy, their individual orbits contributing to the grand rotation that maintains the spiral pattern and the overall structure of the system. The stars and gas we observe in Andromeda, all the light-emitting matter that makes the galaxy visible, represents only a small fraction of its total mass. The vast majority of the matter in and around Andromeda does not emit, absorb, or reflect electromagnetic radiation in any detectable way. This dark matter, inferred only through its gravitational effects, provides the underlying scaffold around which the visible galaxy has assembled, and understanding its distribution and properties remains one of the most important goals in studying Andromeda and galaxies in general. The first hints of dark matter came from studying the rotation curves of galaxies, plots showing how orbital velocity varies with distance from the galactic center. In a simple model, where visible matter dominates the mass, you would expect orbital velocities to decrease with distance once you move beyond most of the galaxy's mass. Following Kepler's laws, just as planetary orbital velocities decrease with distance from the Sunday. However, observations of Andromeda and other spiral galaxies show that rotation velocities remain roughly constant or decline only slightly, even at large distances from the center, implying the presence of significant mass beyond the visible disk. This flat rotation curve indicates that Andromeda sits within an extended halo of dark matter whose mass continues to grow even at radii where little visible matter exists. The distribution of this dark matter can be modeled using various approaches. N-body simulations, computational experiments that track the gravitational interactions of millions or billions of particles over cosmic time, suggest that dark matter halos should have specific density profiles, typically following something approximating a Navarro-Frenk-White profile, where density decreases with radius but extends to very large distances. These halos are not perfectly spherical but somewhat flattened or even triaxial, shaped by the mergers and interactions that occurred during their formation. The visible galaxy forms at the center of this dark matter distribution, with baryonic matter, normal matter made of protons, neutrons, and electrons, falling into the gravitational potential well and cooling to form stars and gas structures. Estimating the total mass of Andromeda's dark matter halo requires careful observations and modeling. One approach uses the motions of satellite galaxies orbiting Andromeda as tracers of the gravitational potential. These small galaxies, bound to Andromeda by gravity but at large distances from the center, orbit through the halo, and their velocities reflect the total enclosed mass. By measuring the positions and velocities of Andromeda's satellites and applying dynamical modeling, astronomers can estimate the mass of the halo at different radii. Current estimates suggest the dark matter halo extends to at least 600,000 light-years from the galactic center and may contain more than 1 trillion solar masses, dominating the total mass budget of the system. Another method for probing dark matter involves gravitational lensing, the bending of light from background objects by foreground mass. While Andromeda is too close and the mass concentration not strong enough for dramatic strong lensing effects, subtle weak lensing signatures can potentially be detected by measuring tiny distortions in the shapes of distant background galaxies seen through Andromeda's halo. These measurements remain technically challenging, but promise to provide independent constraints on the dark matter distribution. The nature of dark matter itself remains mysterious, despite decades of experimental searches and theoretical work. The leading hypothesis suggests dark matter consists of exotic particles that interact only through gravity and possibly the weak nuclear force, but not through electromagnetism or the strong nuclear force. These weakly interacting massive particles, or WIMPs, would have been produced in the early universe and would now pervade space, passing through normal matter with almost no interaction. Alternative theories propose that dark matter consists of primordial black holes formed in the first moments after the Big Bang, or that it represents modifications to gravity itself rather than a new form of matter, though these alternatives face significant theoretical and observational challenges. Whatever its nature, dark matter played a crucial role in galaxy formation throughout cosmic history. In the early universe, before the first stars formed, dark matter began collapsing under its own gravity, creating gravitational potential wells into which normal matter could fall. The dark matter provided the gravitational seeds around which galaxies grew, and it continues to dominate the gravitational dynamics of galaxies today. Without dark matter, galaxies as we observe them could not exist. Their rotation would tear them apart, and large-scale structure in the universe would never have formed. The interaction between dark matter and normal matter in galaxy evolution is subtle and complex. While dark matter provides the gravitational potential, it does not experience friction or pressure and cannot radiate away energy through electromagnetic processes. Normal matter, by contrast, can cool and collapse into dense structures, can form stars that convert mass into energy, and can be redistributed through supernovae and other energetic processes. The visible galaxy represents the result of this complex interplay, shaped by both the dark matter distribution and the physics of gas cooling, star formation, and stellar feedback. As Andromeda and the Milky Way approach each other, their dark matter halos are already beginning to interact, though the stars and gas within each galaxy remain far apart. The halos extend so far that they likely already overlap at their outer edges, creating a gravitational environment more complex than would exist if each galaxy were truly isolated. This interaction will intensify as the galaxies approach, eventually leading to a merger not just of the visible components but of the dark matter halos themselves, creating a single, larger halo within which the remnant galaxy will reside. Understanding dark matter in Andromeda means understanding the invisible foundation of galactic structure, the hidden architecture that has shaped everything we can observe. As you contemplate this dark scaffold, this vast distribution of invisible mass that outweighs the visible galaxy by factors of 10 or more, consider how much of the universe remains hidden from direct view, known only through its gravitational influence, its effects on the motion and distribution of the matter and energy we can see. At the very center of Andromeda, precisely coinciding with the point around which the entire galaxy rotates, lies an object so dense that nothing can escape its gravitational pull once crossed within a certain boundary. This supermassive black hole, containing approximately 100 to 200 million times the mass of our Sun, compressed into a region smaller than our solar system, dominates the gravitational environment of the inner galaxy and likely played a crucial role in the galaxy's formation and evolution. Though the black hole itself is invisible, emitting no light and revealing its presence only through its effects on nearby matter, it represents one of the most important components of Andromeda's structure. The existence of this central black hole was inferred through observations of stellar motions in the galactic core. Stars orbiting very close to the galactic center move at extraordinarily high velocities, velocities that can only be explained if they are orbiting an extremely massive, compact object. By tracking these stellar orbits over time and applying the laws of orbital mechanics, astronomers calculated the mass and position of the central black hole with increasing precision. The black hole's mass is significantly larger than the approximately 4 million solar mass black hole at the center of our own Milky Way, reflecting Andromeda's larger total stellar mass and suggesting a relationship between galaxy mass and central black hole mass that appears to hold across a wide range of galaxy types. Black holes form when matter becomes so concentrated that gravitational collapse becomes inevitable. For stellar mass black holes, this occurs when massive stars exhaust their nuclear fuel and their cores collapse catastrophically in supernova explosions. But supermassive black holes like the one in Andromeda's center require a different formation mechanism, one that can accumulate millions or hundreds of millions of solar masses. The most likely scenario involves the merger of many smaller black holes and the accretion of gas over billions of years, a process intimately connected with the galaxy's growth. Some theories suggest that supermassive black holes may have formed very early in cosmic history from the direct collapse of massive gas clouds, providing seeds around which galaxies subsequently assembled. The region immediately surrounding the black hole, though extremely small compared to the galaxy as a whole, is dynamically complex and physically extreme. Matter falling toward the black hole doesn't plunge directly in but first forms an accretion disk, a swirling disk of gas and plasma heated to millions of degrees by friction and compression. In active galactic nuclei, where large amounts of matter are being actively accreted, these disks shine brilliantly across the electromagnetic spectrum, sometimes outshining the entire rest of the galaxy. Andromeda's central black hole appears to be relatively quiet currently, accreting matter only slowly. But X-ray observations reveal some activity, suggesting that gas continues to fall onto the black hole at a modest rate. The gravitational influence of the black hole extends well beyond the accretion disk, shaping the orbits of stars within the central few light-years of the galaxy. This region, called the nuclear star cluster, contains a dense concentration of stars whose orbits are randomized by gravitational interactions with each other and perturbed by the black hole's gravity. Some stars follow highly elongated elliptical orbits that bring them very close to the black hole at closest approach before carrying them back out to larger distances. These close approaches subject stars to enormous tidal forces that can, in extreme cases, tear the star apart in what astronomers call a tidal disruption event, an occurrence that produces a brief but brilliant flare of radiation as stellar material is shredded and accreted onto the black hole. Interestingly, observations of Andromeda's core have revealed an unusual structure. Rather than a single, centrally concentrated nucleus, Andromeda appears to have two bright points in its very center, separated by just a few light-years. The leading explanation for this double nucleus involves the black hole and a surrounding disk of stars. The black hole itself sits at one of the bright points, while the other represents a concentration of stars in an eccentric, off-center orbit around the black hole. This configuration might have resulted from a past merger with a smaller galaxy, an event that disrupted the symmetry of the central region and created this peculiar structure that persists today. The relationship between supermassive black holes and their host galaxies extends beyond mere coincidence. Observations of many galaxies have revealed correlations between black hole mass and properties of the galactic bulge, such as its total stellar mass and the velocity dispersion of stars within it. These correlations suggest that black holes and galaxies evolve together through feedback processes. When black holes accrete matter vigorously, the enormous energy released can drive powerful winds and jets that blow gas out of the central regions, potentially halting star formation throughout the galaxy. This feedback may be what prevents galaxies from forming stars too efficiently, helping to explain why galaxies convert only a small fraction of their total gas into stars over cosmic time. As the Milky Way and Andromeda approach each other over the next several billion years, Their central black holes will be drawn together by gravity. After the galaxies merge and the stars settle into a new configuration, the two black holes will orbit each other at progressively smaller separations, their orbital energy carried away by gravitational waves until they finally merge in a cataclysmic event that will send ripples through space-time. The merged black hole will contain the combined mass of both progenitors, approximately 200 million solar masses, and will continue to shape the central regions of the remnant galaxy just as its parents shaped Andromeda and the Milky Way. As you imagine this dark heart at Andromeda's center, this point where gravity becomes so extreme that space itself is warped beyond recognition, consider the role these objects play in cosmic evolution. They are not merely curiosities or cosmic hazards, but integral components of galactic structure, intimately connected to the formation and evolution of the galaxies that host them. Their presence felt through gravitational influence, extending far beyond their immediate vicinity. Andromeda does not travel through space alone. Like the Milky Way, it is accompanied by a retinue of smaller satellite galaxies, dwarf galaxies bound by gravity to orbit the larger galaxy, and by tidal streams, long rivers of stars torn from satellites by Andromeda's gravitational tides and stretched across the sky. These companions and their remnants provide crucial information about how galaxies grow through hierarchical merging, how dark matter is distributed on small scales, and what fate awaits small galaxies that venture too close to their larger neighbors. The most prominent satellites of Andromeda are M32 and M110, both classified as dwarf elliptical galaxies, and both easily visible in amateur telescopes near Andromeda in the sky. M32, also called NGC 221, is a compact elliptical galaxy containing perhaps 1 billion stars, a tiny fraction of Andromeda's stellar population, but still a substantial galaxy in its own right. It appears to be in close proximity to Andromeda, projected against the galaxy's disk in our view, and may be on a plunging orbit that will eventually carry it through Andromeda's disk. Some researchers have suggested that M32 might once have been a much larger spiral galaxy that has had its outer regions stripped away by tidal forces during previous close passages, leaving only the dense core we observe today. M110, or NGC 205, is a larger dwarf elliptical located on the other side of Andromeda from M32. It shows evidence of recent or ongoing star formation, unusual for elliptical galaxies, which typically contain only old stellar populations. This star formation might have been triggered by tidal interactions with Andromeda, with gravitational forces compressing gas clouds and initiating the collapse that leads to new star formation. The fate of both M32 and M110 is almost certainly to merge with Andromeda eventually, though whether this will happen before or after Andromeda's collision with the Milky Way depends on their exact orbital parameters. Beyond these bright companions, surveys have identified dozens of dwarf spheroidal galaxies orbiting Andromeda at various distances. Small systems, containing perhaps millions to hundreds of millions of stars, and dominated by dark matter to an even greater extent than large galaxies. These faint systems are difficult to detect because their stars are spread so diffusely across the sky, but careful surveys that look for concentrations of stars with similar distances and motions have steadily increased the catalogue of known Andromeda satellites. Each discovery provides a new data point for understanding the population of dark matter subhalos predicted to exist around large galaxies by cosmological simulations. The distribution of these satellites around Andromeda is not random. Many lie in a plane roughly aligned with Andromeda's disk, forming what astronomers call a plane of satellites. This configuration is surprising because dark matter simulations generally predict that satellites should be distributed more isotropically, randomly scattered around the host galaxy. The existence of this plane has been debated, with some researchers suggesting it might be a temporary configuration that will dissolve over time, while others propose it might indicate something important about how satellite galaxies are accreted or about the nature of dark matter itself. Tidal streams represent the ghosts of former satellite galaxies, long filaments of stars pulled from their parent systems by Andromeda's gravity and spread along orbital paths around the larger galaxy. As a satellite orbits through Andromeda's halo, differential gravitational forces, tidal forces, pull more strongly on the side of the satellite nearest to Andromeda than on the far side. stretching the satellite along its orbital path. Over time, stars escape from the satellite and form leading and trailing tidal tails that mark the orbit. Eventually, the satellite may be completely destroyed, leaving only these stellar streams as evidence that a galaxy once existed there. Several prominent tidal streams have been discovered around Andromeda through careful surveys that map individual stars across large areas of the sky. The giant stellar stream, discovered in the early 2000s, is one of the most spectacular examples, a river of stars stretching across more than 100 degrees of sky as seen from Earth, corresponding to hundreds of thousands of light years in physical space. The stars in this stream share similar motions and chemical compositions, confirming they originated from a single progenitor galaxy that was disrupted billions of years ago. Other streams and stellar clouds in Andromeda's halo likely represent other destroyed satellites, their original structures obliterated, but their constituent stars preserved as fossils of ancient mergers. These tidal features provide powerful tests of our understanding of galactic dynamics and dark matter. The shapes and motions of tidal streams depend sensitively on the gravitational potential through which the progenitor satellite orbited, meaning they carry information about the distribution of dark matter in Andromeda's halo. By modeling the streams and comparing the predictions with observations, researchers can constrain how dark matter is distributed and how it affects the evolution of satellite systems. Some streams show kinematic features or structural details that are difficult to explain with simple models, suggesting that either the dark matter distribution is more complex than assumed, or that multiple merger events have occurred in close succession, creating overlapping structures. The hierarchical merger scenario for galaxy formation predicts that large galaxies like Andromeda should have grown substantially through the accretion of smaller systems over cosmic time. The satellite galaxies and tidal streams we observe represent this process caught in the act. Some mergers completed long ago with only tidal streams remaining, others still in progress, with satellite galaxies being gradually torn apart, and still others, yet to begin with, satellites still intact, though orbiting inexorably toward eventual disruption. The chemical compositions of stars in different streams and satellites provide clues about when and how they formed, with some showing the metal-poor compositions characteristic of early universe star formation, while others contain more enriched stellar populations suggesting more recent formation. Comparing Andromeda's satellite system with the Milky Way's provides insights into how typical or unusual either system might be. The two galaxies have similar numbers of bright satellites but may differ in the total number of faint dwarfs, though observational biases make direct comparison difficult since we are searching for satellites from different vantage points. Both show evidence of planes of satellites, though the significance and persistence of these features remain debated. Both have tidal streams indicating past and ongoing mergers, suggesting that hierarchical growth through accretion of smaller systems is indeed a universal feature of large galaxy evolution. As you imagine these rivers of stars flowing through the darkness around Andromeda, these remnants of galaxies consumed in the endless gravitational dance, consider how galaxy growth is not a smooth process but a violent, chaotic one, where smaller systems are captured and destroyed, their stars redistributed into the halo, their dark matter halos absorbed into the larger dark matter structure. What we see today represents a snapshot of an ongoing process that has been occurring since Andromeda first formed, and will continue until its merger with the Milky Way creates an even larger system with an even more complex merger. History. Andromeda, like all spiral galaxies, rotates. Not as a solid body where every point moves at the same angular velocity, but differentially, with inner regions completing orbits faster than outer regions. This differential rotation creates the dynamic environment in which spiral density waves can exist and persist. And understanding the rotation curve and the forces that maintain it provides fundamental insights into galactic structure and evolution. The rotation of Andromeda can be measured by observing the Doppler shifts of emission from stars and gas at different locations in the galaxy. On one side of the galaxy, material moves toward us, and its light is blue shifted to shorter wavelengths. On the opposite side, material moves away, and its light is red shifted to longer wavelengths. By measuring these shifts and accounting for Andromeda's overall motion relative to us and for the galaxy's inclination angle, astronomers can construct a rotation curve showing orbital velocity as a function of distance from the galactic center. In the very center of Andromeda, rotation velocities increase steeply with radius, reflecting the concentrated mass of the bulge and the central black hole. At distances of a few hundred light-years from the center, orbital velocities reach several hundred kilometers per second. Moving outward through the disk, the rotation curve flattens, with velocities remaining roughly constant or declining only slowly, even at radii, where most of the visible matter has been left behind. This flat rotation curve at large radii provides some of the strongest evidence for dark matter, indicating that mass continues to increase with radius even where we see few stars or little gas. The orbital period for matter at different radii varies dramatically. In the inner galaxy, near the bulge, orbital periods might be just a few tens of millions of years. Our Sun, located in the Milky Way's disk at a distance of about 26,000 light-years from the galactic center, takes approximately 230 million years to complete one orbit. Stars at the edge of Andromeda's visible disk take even longer, perhaps 500 million years or more for a single revolution. These timescales are long compared to human experience, but short compared to the age of the galaxy. Andromeda has completed dozens of rotations since it formed, and stars in the inner disk have orbited hundreds of times. Differential rotation creates shear in the galactic disk, stretching and distorting structures that form within it. If spiral arms were simply material structures, this shear would wind them up tightly within a few rotation periods, creating many tightly wound arms rather than the few prominent arms we observe. The fact that spiral structure persists suggests that the arms are not material but patterns, density, waves that move through the disk at a different speed than the stars and gas themselves. This density wave theory, developed by C. Lin, and Frank Xu in the 1960s, explains how spiral structure can be long-lived in galaxies despite differential rotation. Density waves work somewhat like traffic jams on a highway. Cars, or stars, move at different speeds, depending on their distance from the center. But when they enter a region of increased density, the density wave, they slow down due to the increased gravitational pull. This creates a persistent region of higher density that rotates at its own pattern speed, different from the orbital speeds of individual stars. As stars pass through these regions, they experience gravitational perturbations that can affect their orbits slightly, and gas clouds are compressed, potentially triggering star formation. This is why spiral arms appear bright. They contain concentrated gas and dust where stars are forming, and these young stars are bright and blue. The spiral pattern itself can be reinforced by resonances, locations in the disk where the orbital frequency of stars matches some multiple or fraction of the pattern speed of the density wave. These resonances create preferred locations for spiral features and can help explain the structure and persistence of spiral arms. Different types of resonances exist at different radii, including corrotation resonance, where stars orbit at the same speed as the pattern speed, inner and outer Lindblad resonances, where the epicyclic frequency of stellar orbits matches the pattern speed, and higher-order resonances that can create more complex structures. The rotation of Andromeda also affects how we observe it. Because the galaxy is tilted relative to our line of sight, one side rotates toward us and the other away, creating a velocity gradient across the galaxy's image. This makes it possible to measure rotation even though we see the galaxy from outside, something that would be difficult for a galaxy oriented exactly face onto us. The rotational velocity we measure must be corrected for this inclination to determine the true orbital speeds of stars and gas. Andromeda's rotation is not perfectly smooth and symmetric. Perturbations from satellite galaxies create ripples and warps in the disk. The spiral arms themselves represent departures from perfect axial symmetry. The bar structure that some observations suggest might exist in Andromeda's inner regions would create additional, non-axisymmetric features in the gravitational potential and affect the rotation pattern. These complications make Andromeda a dynamically rich system, where the interplay of various forces creates complex structure and evolution. As the galaxy rotates, stars follow approximately elliptical orbits around the galactic center, orbits that can be nearly circular for stars in the disk, or highly elongated for stars in the bulge or halo. These orbits are not fixed but precess, their orientations slowly rotating over time due to the non-spherical distribution of mass in the galaxy. The orbits are also subject to perturbations from spiral arms, encounters with molecular clouds, and interactions with other stars. Though actual close encounters between stars are extremely rare, even in the relatively dense environment of the galactic disk. Understanding the rotation and dynamics of Andromeda helps us understand how galaxies work, how structure persists over billions of years, despite the complexity of gravitational interactions, how gas is funneled towards star-forming regions, and how the galaxy will respond to future perturbations, including the eventual collision with the Milky Way. The dance of matter and gravity that creates this rotating structure follows the same physical laws everywhere in the universe, and what we learn from Andromeda applies to spiral galaxies throughout the cosmos. Within Andromeda's spiral arms and scattered throughout its disk, new stars continue to form from clouds of gas and dust, continuing a process that has been occurring since the galaxy first assembled billions of years ago. This ongoing star formation represents the galaxy's future. Each new star, a nuclear furnace that will shine for millions to trillions of years depending on its mass, and understanding where and how stars form in Andromeda provides crucial insights into the life cycle of galaxies and the chemical evolution of the universe. Star formation begins in giant molecular clouds, vast concentrations of cold gas composed primarily of hydrogen molecules, along with trace amounts of helium and heavier elements. These clouds can contain hundreds of thousands or millions of solar masses of material spread across regions hundreds of light years across. Within these clouds exist even denser cores, regions where the gas is concentrated to such high densities that gravity begins to dominate over the internal pressure that normally supports the cloud against collapse. When these cores exceed a critical mass for their temperature and density, gravitational collapse becomes inevitable and star formation begins. The trigger for this collapse can come from various sources. The passage of a cloud through a spiral arm compresses it, potentially pushing it over the threshold for gravitational instability. Shockwaves from supernovae can compress nearby clouds, initiating collapse in a kind of self-propagating star formation, where one generation of massive stars triggers the formation of the next. Collisions between clouds can concentrate gas to critical densities. Once collapse begins, it tends to be rapid on astronomical timescales, with stars forming within a few million years from clouds that may have existed in a stable or slowly evolving state for hundreds of millions of years. As a collapsing core contracts, it heats up through the conversion of gravitational potential energy into thermal energy. The center becomes hot and dense enough for nuclear fusion to begin once the temperature exceeds about 10 million Kelvin, at which point hydrogen nuclei have enough kinetic energy to overcome their electrical repulsion and fuse together to form helium, releasing energy in the process. This onset of fusion marks the birth of a new star, an object that has reached hydrostatic equilibrium, where the outward pressure from fusion-generated heat balances the inward pull of gravity. Not all collapsing cores produce single stars. Fragmentation during collapse often results in binary or multiple star systems, with two or more stars orbiting their common center of mass. The excess angular momentum of the original cloud is distributed through the formation of these multiple systems and through the formation of circumstellar disks from which planets may eventually form. Observations of star-forming regions in Andromeda reveal many young binary systems and associations of young stars born from the same molecular cloud, moving through space together before gradually dispersing over tens of millions of years. The most massive stars that form in molecular clouds, those with tens of times the mass of our Sun, burn through their nuclear fuel rapidly and live for only a few million years before exhausting their hydrogen and proceeding through fusion of heavier elements until they can no longer generate sufficient energy to support themselves against gravity. These massive stars end their lives in spectacular supernova explosions that briefly outshine entire galaxies and distribute heavy elements into the surrounding interstellar medium, enriching the gas from which the next generation of stars will form. This chemical enrichment is crucial for the evolution of galaxies and for the eventual formation of planets and life, since the heavy elements produced by stellar nucleosynthesis and released in supernovae provide the raw materials for rocky planets and biological molecules. The rate of star formation in Andromeda can be estimated through several methods. One approach counts the number of young, massive stars visible in ultraviolet or H-alpha images, stars whose short lifespans mean they must have formed recently. Another method measures the infrared emission from dust heated by young stars, emission that correlates with star formation rate, because newly formed stars are typically embedded in dusty regions that absorb their ultraviolet light and re-radiate it in the infrared. These measurements suggest that Andromeda currently forms approximately 1 new solar mass of stars per year, somewhat less than the Milky Way's estimated rate of about 1.5 to 3 solar masses per year. The distribution of star formation across Andromeda is not uniform. Star formation concentrates in the spiral arms, where gas densities are higher, and compression from the density wave triggers collapse. Within the arms, star formation occurs in discrete complexes, each containing multiple star-forming regions and associations of young stars. These complexes have their own internal structure, with the most massive stars forming in the densest regions, and lower mass stars forming more widely distributed around them. The massive stars, through their intense radiation and stellar winds, eventually disrupt the remaining gas in their birth clouds, halting further star formation and dispersing the cloud. This feedback limits how efficiently molecular clouds can convert their gas into stars, with typical star formation efficiencies of only a few % before the cloud is dispersed. Comparing star formation in Andromeda with other galaxies reveals patterns that help us understand what controls the rate and efficiency of this process. Galaxies with more gas tend to form stars more rapidly, though the relationship is not strictly linear. The density and temperature of the gas matter, with cooler, denser gas forming stars more efficiently. The presence of spiral structure helps by concentrating gas and triggering collapse. Environmental factors like interactions with other galaxies or with the intergalactic medium can either enhance star formation by compressing gas or suppress it by heating gas or stripping it from the galaxy entirely. As you imagine these stellar nurseries scattered throughout Andromeda, these regions where gravity gathers gas into dense cores that ignite into new suns, consider the continuous cycle of birth and death that characterizes galactic evolution. Stars form from gas enriched by previous generations of stars, live for timescales ranging from millions to trillions of years depending on their mass, and return much of their material to the interstellar medium through stellar winds and explosive deaths. This cycle drives the chemical evolution of galaxies, progressively enriching the gas with heavy elements and changing the properties of successive stellar generations. The space between stars in Andromeda is not empty but filled with tenuous gas and dust, an interstellar medium that comprises a significant fraction of the galaxy's baryonic matter and plays a crucial role in galaxy evolution. This medium exists in multiple phases, with different temperatures, densities, and physical properties. And the interactions between these phases, and with stars, drive much of the visible activity in the galaxy. The most abundant component of the interstellar medium is hydrogen, the simplest and most common element in the universe, existing in various forms depending on local conditions. In the coldest, densest regions, hydrogen forms molecules H2, creating the giant molecular clouds where stars form. In warmer regions, hydrogen remains atomic, He, detectable through its 21 centimeter radio emission that results from a quantum mechanical transition in the hydrogen atom's ground state. In hot regions near young massive stars or supernova remnants, hydrogen becomes ionized, H-, stripped of its electron by high-energy photons, creating H2 regions that glow in visible light from recombining hydrogen atoms. Helium is the second most abundant element, making up about 25% of the interstellar medium's mass, while all heavier elements combined contribute only about 1 to 2%. Despite their low overall abundance, these heavy elements astronomers call them metals, regardless of their actual chemical properties, play disproportionately important roles. Carbon, oxygen, and other elements form molecules and contribute to cooling processes that allow gas clouds to contract. Dust grains composed of silicates, carbon, and ices form in the atmospheres of dying stars and provide surfaces where molecules can form through chemistry that would be inefficient in the gas phase. These dust grains also absorb and scatter light, creating the dark lanes visible in images of Andromeda, where dust clouds block the light of background stars. The interstellar medium exists in rough pressure equilibrium, meaning different phases with different temperatures and densities coexist with similar pressures. Cold molecular clouds have temperatures of just 10 to 30 Kelvin, but densities of hundreds to thousands of particles per cubic centimeter. Warm neutral atomic hydrogen has temperatures around 5,000 to 8,000 Kelvin and densities of about 0.1 to 1 particles per cubic centimeter. Warm ionized gas exists at similar temperatures but lower densities. Hot ionized gas, heated by supernovae and stellar winds, reaches temperatures of millions of Kelvin but has very low densities, less than 0.01 particles per cubic centimeter. These phases continuously exchange mass and energy through various processes. Supernova explosions inject enormous amounts of energy into the interstellar medium, creating expanding shells of hot gas that sweep up surrounding material and compress it into dense shells. As these supernova remnants expand and cool over hundreds of thousands of years, the hot gas radiates away its energy and eventually merges with the general warm medium. The radiation from massive stars ionizes surrounding gas, creating bubbles of hot, ionized gas that can expand and merge with other bubbles. Cooler gas can condense out of warmer phases, accumulating in regions where the density is slightly higher and forming clouds that may eventually become sites of star formation. The distribution of gas in Andromeda is not uniform but shows complex structure on all scales, from galaxy-wide gradients to tiny turbulent eddies within molecular clouds. Gas concentrates in the spiral arms, where compression by the density wave increases the density and triggers the formation of molecular clouds and subsequent star formation. Between the arms, gas exists primarily in more diffuse atomic and ionized forms. The central regions of the galaxy are largely depleted of gas, most of it having been converted into stars over billions of years or driven out by feedback from star formation and black hole accretion. The outer disk contains substantial amounts of gas, including a warp, where the disk is not perfectly flat, but tilted relative to the inner galaxy, a feature likely caused by gravitational interactions with satellite galaxies. Radio telescopes observing the 21-centimeter emission from neutral hydrogen have mapped the gas distribution in Andromeda in great detail, revealing not just the concentration in spiral arms, but also the kinematics of the gas, how it moves and rotates through the galaxy. This gas follows generally circular orbits similar to the stars, though with some radial motions where gas flows inward or outward, driven by spiral arm gravitational forces or by feedback from star formation. The velocity structure of the gas provides information about the gravitational potential and about non-gravitational forces acting on the gas. Magnetic fields thread through the interstellar medium, revealed through observations of polarized light and radio emission. These fields, though weak by laboratory standards, measuring microgauss, millionths of the field strength of a refrigerator magnet, are dynamically important because the ionized component of the interstellar medium couples to them. Magnetic fields can provide support against gravitational collapse, can channel flows of ionized gas, and can accelerate cosmic rays, high-energy particles that pervade the galaxy and contribute to heating and ionizing the interstellar medium. The interstellar medium also contains cosmic rays, charged particles, mostly protons, accelerated to relativistic energies by supernovae and other energetic processes. These particles spiral along magnetic field lines and diffuse throughout the galaxy, gradually losing energy through interactions with gas and magnetic fields. Cosmic rays contribute to the pressure of the interstellar medium and affect the chemistry of molecular clouds by ionizing molecules and initiating chains of chemical reactions. Understanding the interstellar medium in Andromeda is crucial for understanding galaxy evolution because this medium represents both the reservoir from which future stars will form and the repository for material returned by dying stars. The balance between gas consumption through star formation and gas replenishment through stellar mass loss, supplemented by accretion of fresh gas from the intergalactic medium, determines how long a galaxy can continue forming stars. The properties of the interstellar medium also affect how stars form, with the temperature, density, and chemical composition of gas clouds influencing the masses and properties of the stars that form from them. As you contemplate this tenuous but crucial component of Andromeda, this medium that fills the spaces between the stars with substance and activity, consider how even in the apparent emptiness of space, matter and energy interact in complex ways that shape the evolution of galaxies and create the conditions necessary for stars, planets, and ultimately life to emerge. Our understanding of Andromeda comes from observations across the entire electromagnetic spectrum, from radio waves meters long to gamma rays with wavelengths shorter than atomic nuclei. Each wavelength band reveals different physical processes and different components of the galaxy, and the comprehensive picture we have today results from combining observations from many telescopes and instruments operating across this vast range of wavelengths. At radio wavelengths, telescopes detect the 21-centimeter emission from neutral hydrogen that traces the distribution and kinematics of atomic gas throughout the galaxy. Radio continuum emission reveals synchrotron radiation from cosmic rays spiraling in magnetic fields and thermal emission from ionized gas in H2 regions. Molecular lines including carbon monoxide, co-emission, trace the densest molecular clouds where stars form. Radio observations can penetrate dust that blocks visible light, making them essential for studying obscured regions, including the galactic center and dense molecular clouds. The Very Large Array in New Mexico and the Westerbork Synthesis Radio Telescope in the Netherlands have produced detailed radio maps of Andromeda showing its gas distribution and magnetic field structure. Moving to infrared wavelengths, we detect thermal emission from dust heated by stars and see through dust clouds to observe star formation regions that are invisible in optical light. Near-infrared observations at wavelengths of 1 to 3 micrometers show light from cool red giant stars and penetrate dust moderately well. Mid-infrared observations at 5 to 40 micrometers detect emission from dust at temperatures of a few hundred Kelvin, dust heated by young stars in star-forming regions. Far-infrared observations at 50 to 500 micrometers reveal colder dust associated with the interstellar medium and map the distribution of material that will fuel future star formation. The Spitzer Space Telescope and the Herschel Space Observatory have provided spectacular infrared views of Andromeda, revealing its star formation activity and dust distribution in unprecedented detail. Optical observations using visible light have the longest history, dating back to the first telescopic observations of the Andromeda Nebula in the 17th century. Optical light primarily traces stellar populations, with different colors revealing different types of stars. Blue light comes from hot, massive young stars and traces recent star formation. Red light comes from cooler, older stars and dominates in the bulge and older disk regions. Careful photometry, measuring the brightness of individual stars, allows construction of color magnitude diagrams that reveal stellar populations and ages. Spectroscopy, splitting light into its component wavelengths, measures the chemical compositions of stars, the velocities of stars and gas through Doppler shifts, and identifies emission and absorption features that reveal physical conditions. Ground-based observatories and the Hubble Space Telescope have resolved millions of individual stars in Andromeda, creating detailed maps of stellar populations across the galaxy. Ultraviolet observations detect the hottest stars, young massive stars whose surfaces reach temperatures of tens of thousands of Kelvin and emit most of their light in the ultraviolet. These observations trace the most recent star formation, stars so young that many may still be embedded in their birth clouds or have recently emerged. Ultraviolet light also reveals hot gas in the interstellar medium and can detect the outer atmospheres of evolved stars. The Galaxy Evolution Explorer, GALEX, spacecraft mapped Andromeda in ultraviolet light, providing a census of its young stellar population and revealing structure in the spiral arms where star formation is concentrated. X-ray observations detect the most energetic processes in the galaxy. X-ray binaries, systems where a neutron star or black hole accretes matter from a companion star, shine brightly in X-rays, as infalling matter is heated to millions of Kelvin. Supernova remnants emit X-rays from shocked gas. The hot phase of the interstellar medium, gas heated to millions of Kelvin by supernovae and stellar winds, produces diffuse X-ray emission. The supermassive black hole at Andromeda's center, though relatively quiet, can be detected in X-rays from its weak accretion activity. The Chandra X-ray Observatory and XMM Newton satellite have catalogued thousands of X-ray sources in Andromeda, studying everything from accreting compact objects to the diffuse hot gas that pervades the galaxy. Gamma-ray observations detect the highest energy photons, though Andromeda is relatively faint in gamma rays compared to more active galaxies. Gamma rays can result from the decay of radioactive elements produced in supernovae, from interactions of cosmic rays with the interstellar medium, or from exotic processes involving dark matter annihilation. The Fermi Gamma Ray Space Telescope has detected Andromeda in gamma rays, providing constraints on cosmic ray populations and potential dark matter signals. Each of these wavelength bands requires different telescope technologies because the same mirrors and detectors don't work across the entire spectrum. Radio telescopes use large dish antennas or arrays of antennas to collect and focus radio waves. Infrared telescopes require cooling to prevent their own thermal emission from overwhelming celestial signals. Optical and ultraviolet telescopes can use conventional mirrors but must be placed in space to avoid atmospheric absorption in the ultraviolet. X-ray telescopes require special grazing incidence mirrors because X-rays would penetrate conventional mirrors. Gamma-ray detectors convert gamma rays into charged particles that can be tracked to determine the original photon's direction and energy. Combining observations across all these wavelengths creates a comprehensive view of Andromeda that no single wavelength could provide. The distribution of stellar populations, the locations and activity of star-forming regions, the structure of the interstellar medium, the high-energy processes occurring throughout the galaxy, and the overall dynamical state all come into focus when we integrate information from radio to gamma rays. This multi-wavelength approach has become standard in modern astronomy, recognizing that galaxies are complex systems where multiple physical processes operate simultaneously and where no single observation technique can capture the full picture. As technology continues to advance, new telescopes with greater sensitivity and resolution come online, promising ever more detailed views of Andromeda. The James Webb Space Telescope provides infrared observations with unprecedented resolution, resolving individual stars in crowded regions and penetrating dust to reveal hidden structures. Future extremely large telescopes with mirrors 30 to 40 meters in diameter will resolve finer details and detect fainter objects. New radio telescope arrays will map gas and magnetic fields with higher fidelity. Each technological advance brings new discoveries and deeper understanding of this nearby galaxy that serves as a laboratory for studying galactic structure and evolution. When Andromeda first formed in the early universe, its gas consisted almost entirely of hydrogen and helium, the elements created in the Big Bang. Today, approximately 13 billion years later, the gas in Andromeda's disk contains approximately 1 to 2% heavier elements by mass, a composition similar to the Sun's and indicative of billions of years of chemical enrichment through stellar nucleosynthesis. This gradual enrichment of metals, as astronomers call all elements heavier than helium, represents a fundamental aspect of galactic evolution, and tracing how metallicity changes with location and stellar age provides crucial insights into Andromeda's formation history. The process of chemical enrichment begins with star formation. First-generation stars formed from primordial gas contained almost no heavy elements, but during their lifetimes, nuclear fusion in their cores converted hydrogen into helium and, for the most massive stars, helium into progressively heavier elements through carbon, oxygen, neon, magnesium, silicon, and eventually iron. When these stars died, some gently shedding their outer layers in planetary nebulae and others exploding as supernovae, they released this chemically enriched material into the interstellar medium. Subsequent generations of stars formed from this enriched gas, beginning their lives with higher metallicities than their predecessors. Different elements come from different sources. Carbon, nitrogen, and oxygen form in stars of various masses through nucleosynthesis during their lifetimes. Iron peak elements, including iron, nickel, and cobalt, form, primarily in Type I, a supernovae, thermonuclear explosions that occur when white dwarfs in binary systems accrete enough matter from their companions to exceed a critical mass and detonate. Alpha elements like oxygen, magnesium, silicon, and calcium form in massive stars and are released primarily in core collapse supernovae, the explosions that mark the deaths of stars, more than about 8 times the Sun's mass. The heaviest elements, including gold, platinum, and uranium, require special conditions to form, potentially including neutron star mergers where extreme densities and neutron-rich environments facilitate rapid neutron capture, nucleosynthesis. By measuring the relative abundances of different elements in stars of different ages, astronomers can reconstruct the chemical enrichment history of Andromeda and identify which types of stars and supernovae dominated enrichment at different epochs. The ratio of alpha elements to iron, for example, provides information about the relative importance of massive stars, which produce alpha elements, versus type 1, a supernovae, which produce iron. This ratio typically decreases with time, as the contribution from type 1, a supernovae, which have a delay between star formation and explosion, because the white dwarfs must first form and then accrete matter, becomes more significant. Within Andromeda, metallicity varies with location. The inner disk is more metal-rich than the outer disk, reflecting a metallicity gradient that results from star formation being more vigorous and sustained in the inner regions where gas densities are higher. This gradient has important implications for understanding galaxy evolution, suggesting that either star formation efficiency varies with radius, or that radial gas flows have transported metals inward, or both. The bulge contains old, metal-rich stars, indicating that the inner galaxy enriched rapidly early in its history. The halo contains predominantly old, metal-poor stars, including the ancient globular clusters and stars stripped from satellites that formed before significant enrichment had occurred. Stellar populations in Andromeda can be classified not just by their ages but by their metallicities, creating a two-dimensional picture of galactic history. The oldest, most metal-poor stars formed first, before enrichment had progressed significantly. Intermediate-age stars have intermediate metallicities, reflecting the progressive enrichment of the gas from which they formed. The youngest stars have the highest metallicities, formed from gas enriched by billions of years of previous stellar evolution. Exceptions to this pattern occur when metal-poor gas accretes onto the galaxy from the intergalactic medium, or when mergers with metal-poor satellite galaxies add their stellar populations to the halo. Spectroscopy provides the tool for measuring stellar metallicities. By analyzing the absorption lines in stellar spectra, astronomers can determine the abundances of dozens of elements and construct detailed chemical abundance patterns. Different stars show different abundance patterns depending on when and where they formed and what enrichment sources dominated at that time and location. Stars formed in satellite galaxies before they merged with Andromeda may show distinct abundance patterns reflecting different enrichment histories, allowing them to be identified even billions of years after the merger that brought them into Andromeda's halo. The chemical enrichment history of Andromeda can be modeled using chemical evolution models that track how gas is converted into stars, how stars produce and release heavy elements, and how gas flows through the galaxy. These models must account for the initial mass function, the distribution of masses for newly formed stars, the timescales for different types of supernovae, the efficiency of star formation, and the complex gas flows, including accretion from outside the galaxy and ejection through winds driven by star formation and black hole accretion. By adjusting model parameters and comparing predictions with observations of metallicity distributions and abundance patterns, researchers can constrain Andromeda's star formation history and the relative importance of different enrichment processes. Comparing Andromeda's chemical enrichment with that of the Milky Way reveals both similarities and differences. Both galaxies show metallicity gradients in their disks, both have metal-poor halos and metal-rich bulges, and both show abundance patterns, indicating contributions from multiple types of stars and supernovae. The details differ, however, with Andromeda having formed stars somewhat earlier and more rapidly than the Milky Way in some regions, reflected in subtle differences in abundance patterns. These differences provide clues about what conditions and events shaped each galaxy's particular evolutionary path. The future chemical evolution of Andromeda depends on its ongoing star formation and on the eventual merger with the Milky Way. Current star formation continues to enrich the interstellar medium, gradually increasing metallicity over time, though the rate of enrichment is slower now than in the past, because much of the galaxy's gas has already been converted into stars. When Andromeda and the Milky Way merge, Their distinct chemical enrichment histories will be mixed together, and the merger-induced starburst may produce a new generation of stars with metallicities reflecting the combined enrichment from both galaxies. The merge system will continue enriching as long as gas remains available for star formation, eventually reaching higher metallicities than either progenitor galaxy achieved independently. Every star in Andromeda carries within it a record of the conditions that existed when and where it formed, encoded in its chemical composition, its motion through space, and its position within the galaxy. By carefully analyzing these properties across millions of stars, astronomers can reconstruct Andromeda's history, tracing how the galaxy formed, how it has evolved over billions of years, and what events have shaped its current structure. This archaeological approach to galactic history treats stars as fossils, ancient objects that remember the past even though the conditions that formed them have long since changed. The oldest stars in Andromeda, those in the halo and the ancient globular clusters, formed within the first billion years or so after the Big Bang, when the universe was less than 10% of its current age. These stars are metal-poor because they formed from gas that had experienced little previous enrichment, gas still dominated by primordial hydrogen and helium. Their chemical compositions provide snapshots of the early universe's composition, and their dynamical properties reveal how the galaxy's halo assembled. Many halo stars likely originated not in Andromeda itself, but in smaller protogalaxies that merged to build the larger system. A hierarchical assembly process, predicted by cosmological simulations and now confirmed through observations of tidal streams and chemically distinct stellar populations. The globular clusters orbiting Andromeda provide particularly clear windows into the early history. These dense stellar systems formed early and have remained largely intact since their formation, preserving their original stellar populations with minimal contamination from later generations. By measuring the ages of globular clusters through comparison of their color magnitude diagrams with stellar evolution models, astronomers can determine when they formed. Most of Andromeda's globular clusters appear to be ancient, with ages exceeding 10 billion years, though some show evidence of being younger, potentially formed during later merger events or in bursts of star formation triggered by galactic interactions. Interestingly, globular clusters in Andromeda show a curious bimodal metallicity distribution, clustering into two populations: metal-poor clusters with compositions similar to the halo stars, and metal-rich clusters with compositions more similar to the thick disk. This bimodality might reflect two distinct formation epochs or environments, with metal-poor clusters forming first in protogalactic fragments and metal-rich clusters forming later in the merged system after significant enrichment had occurred. Alternative explanations suggest the metal-rich clusters might have originated in dwarf galaxies that merged with Andromeda, bringing their own globular cluster populations with them. The bulge of Andromeda contains old, metal-rich stars, a population that appears to have formed rapidly early in the galaxy's history through a vigorous burst of star formation. This rapid bulge formation converted a large fraction of the central gas into stars within perhaps the first billion or 2 years of the galaxy's existence, creating the dense stellar concentration we observe today. The exact mechanism that drove this early bulge formation remains debated, with possibilities including dissipative collapse where gas fell into the central potential well and formed stars efficiently, or through the merger of several gas-rich protogalaxies whose interaction funneled gas to the center where it formed stars. The disk presents a more complex story. While some disk stars are nearly as old as the bulge, others formed progressively over the galaxy's lifetime, creating the age gradient observable today, where the inner disk contains older stars on average than the outer disk. This inside-out growth pattern suggests that Andromeda's disk assembled gradually, with the inner regions forming stars first and the disk extending outward over time as gas accreted onto the galaxy and settled into the rotating disk. Spiral structure likely existed throughout much of this history, facilitating star formation through density, wave compression, and creating the organized rotation we observe today. Evidence for past merger events appears throughout Andromeda's structure. The tidal streams discussed earlier represent relatively recent mergers, satellites disrupted within the last few billion years, but earlier mergers have left subtler signatures. Kinematic substructure in the halo, groups of stars moving together in ways that suggest common origin, indicates past accretion events. Chemical abundance patterns that differ from the bulk population suggest stars formed elsewhere and later incorporated into Andromeda. Even the disk shows features that might reflect past interactions, including warps and asymmetries potentially caused by satellite passages. One particularly intriguing feature is the possible existence of a second disk component, sometimes called the thick disk, lying above and below the main thin disk. Stars in this thick disk have higher velocity dispersions, moving more randomly rather than in organized rotation, and different chemical abundances than thin disk stars, suggesting they formed earlier or in different conditions. The thick disk might represent stars formed during an early, more chaotic phase of disk assembly, or it might consist partially of stars heated by past merger events that injected energy into the disk and puffed it up vertically. The star formation history of Andromeda can be reconstructed by analyzing the stellar populations visible today and working backward to determine when these stars must have formed. This reconstruction suggests that Andromeda formed stars vigorously early in its history, with star formation rates perhaps several times higher than today when the galaxy was young and gas-rich. The rate declined over time as gas was consumed by star formation and as feedback from supernovae and the central black hole potentially expelled gas from the galaxy or heated it to temperatures where it could not efficiently cool and collapse. The current relatively modest star formation rate of approximately 1 solar mass per year represents a galaxy that has matured, consumed much of its gas, and settled into a more quiescent state. Comparing Andromeda's history with that of the Milky Way reveals interesting parallels and differences. Both galaxies show evidence of early bulge formation, disk assembly over extended periods, and hierarchical growth through mergers. The Milky Way appears to have formed stars somewhat more gradually, while Andromeda had a more intense early phase. These differences likely reflect variations in initial conditions, different merger histories, and perhaps different environmental influences. But both galaxies followed the general pattern of formation and evolution, predicted by our understanding of galaxy formation in a cosmological context. Looking forward, Andromeda's history is not complete. Star formation will continue as long as gas remains available, gradually converting more of the galaxy's reservoir into stars and enriching the remaining gas with heavy elements. The merger with the Milky Way will write a new chapter, disrupting both galaxies' structures, triggering new star formation, and eventually creating a merged elliptical galaxy with its own distinct stellar populations, reflecting both progenitors' histories. The stars that exist today will remember this event, their orbits altered, their kinematics recording the violence of the collision in patterns that future astronomers billions of years hence might decode. As you contemplate this deep history written in stars, this record of 13 billion years preserved in the motions and compositions of 1 trillion suns, consider how astronomy allows us to travel backward in time, not by visiting the past directly, but by reading the evidence it left behind. Every old star is a messenger from the ancient universe, and by collecting enough of these messages and interpreting them carefully, we can reconstruct the story of how galaxies like Andromeda came to be. Andromeda is not stationary in space. The galaxy is moving toward the Milky Way at approximately 110 kilometers per second, a closing velocity that will eventually bring the two galaxies together in a collision that will reshape both systems beyond recognition. This approach is not a recent development, but represents the culmination of billions of years of gravitational interaction. Two galaxies bound in a cosmic dance that began shortly after their formation and will end only when they merge into a single larger system. The motion of Andromeda toward us was first measured precisely in the early 20th century through spectroscopy. Unlike most distant galaxies which show redshifts indicating motion away from us due to the expansion of the universe, Andromeda displays a blue shift, its spectral lines shifted toward shorter wavelengths by the Doppler effect as the galaxy approaches. This measurement revealed that local gravitational forces can overcome cosmic expansion on galactic scales, that Andromeda and the Milky Way are gravitationally bound to each other as members of the local group of galaxies, and that their mutual attraction is pulling them together. The approach velocity of 110 kilometers per second is actually the radial velocity, the component of motion along our line of sight toward or away from us. Andromeda also has a tangential velocity, motion perpendicular to our line of sight, that produces no Doppler shift, but can be measured through precise tracking of Andromeda's position on the sky over many years using the Hubble Space Telescope. These measurements revealed that Andromeda's tangential velocity is relatively small, meaning the galaxy is moving almost directly toward us, rather than on a trajectory that would carry it past us at some distance. This finding confirmed that a collision is indeed inevitable and will occur roughly 4 to 5 billion years from now. The gravitational interaction between Andromeda and the Milky Way has already begun despite the galaxies still being separated by 2.5 million light-years. At this distance, each galaxy exerts a gravitational force on the other, and they have been falling toward each other for billions of years. Computer simulations that model the gravitational dynamics of the local group suggest that Andromeda and the Milky Way may have been on a more distant past collision course, moving away from each other as part of the cosmic expansion before their mutual gravity became strong enough to slow, stop, and reverse their motion. Now they are in the infall phase, accelerating toward each other as gravity pulls them together. The collision will not be a sudden impact where the galaxies smash into each other and rebound. Instead, it will be a long, complex merger lasting several billion years as the two galaxies pass through each other, their gravity distorting each other's structures, stars and gas mixing, and multiple passages occurring before the systems finally settle into a single merged galaxy. During the first close approach, tidal forces will stretch both galaxies, pulling out long tails of stars and distorting the spiral structures. Gas clouds will collide, triggering intense bursts of star formation that will light up the merging system in a brilliant display visible across vast cosmic distances. Simulations of the Andromeda-Milky Way merger show the complex choreography this gravitational dance will follow. After the first passage, the galaxies will separate again, moving apart before gravity pulls them back together for additional encounters. With each passage, more orbital energy is transferred into random motions of stars and into tidal tails that carry away energy and angular momentum. Eventually, after perhaps 2 to 3 billion years of repeated passages, the two galaxies will merge completely into a single elliptical galaxy that astronomers have whimsically nicknamed Milkomeda or Milkdromeda. The fate of individual stars during this merger is surprisingly benign, despite the violence on galactic scales. Stars are so small compared to the distances between them that actual collisions between stars will be extraordinarily rare, perhaps only a handful occurring in each galaxy during the entire merger. Instead, stars will simply pass through the opposing galaxy, their orbits altered by the gravitational potential of the passing galaxy, but the stars themselves unharmed. The solar system, if it still exists in its current form, would likely survive the merger physically intact, though its orbit around the galactic center would be dramatically altered, and it might find itself in a very different galactic environment. The central supermassive black holes in each galaxy will be drawn together during the merger, eventually forming a bound binary black hole system that orbits ever closer as gravitational wave emission carries away orbital energy. The final merger of these black holes will be a cataclysmic event, converting a significant fraction of their combined mass into gravitational wave energy in a burst that will propagate across the universe at the speed of light. This merger will create a single black hole containing the combined mass of both progenitors, approximately 200 million solar masses, and this merged black hole will likely experience a gravitational wave recoil, a kick that might temporarily displace it from the center of the merged galaxy until dynamical friction with surrounding stars drags it back to the center. The merger will trigger intense star formation as gas clouds collide and compress, potentially consuming most of the remaining gas in both galaxies within a few 100 million years and creating a burst of new stars. This starburst phase will make the merging system extremely luminous, visible as a particularly bright galaxy at great distances. After the burst ends and the merger completes, star formation will decline dramatically, and the merged galaxy will fade to the red colors characteristic of elliptical galaxies dominated by old stellar populations. The local group dynamics will also be affected. The merger will create a gravitational center that will attract the smaller galaxies of the local group, including the large and small Magellanic Clouds, the Triangulum Galaxy, M33, and the many dwarf galaxies orbiting Andromeda and the Milky Way. Some of these smaller galaxies may be captured and eventually merge with the remnant, while others might be ejected from the local group entirely through gravitational interactions during the chaotic merger period. As you imagine this slow approach, this billions of years long fall that will reshape our cosmic neighborhood, consider the timescales involved. On human timescales, even on the timescale of our entire species' existence, Andromeda appears stationary, barely moving in the sky. Yet over cosmic time, it draws inexorably closer, growing larger in our night sky, though too slowly for any individual to perceive. Heading toward an appointment with destiny that was set when the two galaxies first formed and found themselves gravitationally bound in the local group. When Andromeda and the Milky Way collide approximately 4.5 billion years from now, the event will transform both galaxies through one of the most dramatic processes in the universe, a major galaxy merger. Understanding what happens during such mergers comes from observations of colliding galaxies throughout the universe, from detailed computer simulations that model the gravitational dynamics, and from theoretical work that describes the physical processes involved. The picture that emerges is one of chaos and beauty, destruction and creation occurring simultaneously on galactic scales. The first close approach will occur when the two galaxies are nearest to each other, perhaps passing within 50,000 light-years or less. At this distance, tidal forces become significant, stretching both galaxies along the line, connecting them and compressing them perpendicular to this line. Stars on the near side of each galaxy feel stronger gravitational pull from the other galaxy than stars on the far side, creating tidal forces that work to pull each galaxy apart. Long tidal tails form, streams of stars pulled from the galaxy's disks and flung into intergalactic space along graceful arcs that mark the orbital path. Gas behaves differently from stars during the collision. While stars pass through each other with negligible probability of actual collision, gas clouds experience ram pressure as they plow through the gas in the other galaxy. This pressure compresses the clouds, raising their densities above the critical threshold for gravitational collapse and triggering intense star formation. The compression is most effective where the gas is densest, in the disk regions where molecular clouds concentrate. So the collision will light up both galaxies with brilliant, new star-forming regions that will glow blue from hot young stars. The induced star formation, often called a starburst because of its intensity and relative brevity, will consume gas at rates perhaps 10 or 100 times higher than the current star formation rates in either galaxy. This rapid consumption will create spectacular displays, with clusters of young stars ionizing surrounding gas to create vast H2 regions visible across intergalactic distances. The most massive stars in these clusters will live only a few million years before exploding as supernovae, and the supernovae rate during the starburst will be correspondingly high, potentially dozens or even hundreds per century compared to perhaps 1 or 2 per century in the Milky Way today. The energy released by this starburst will have consequences for the gas that doesn't immediately form stars. Supernovae and stellar winds from massive stars inject tremendous amounts of energy and momentum into the interstellar medium, creating hot bubbles and driving galactic winds that expel gas from the galaxy entirely. These winds may remove a significant fraction of the gas, limiting how many stars can ultimately form and potentially enriching the intergalactic medium with heavy elements produced in the starburst. The feedback from star formation thus regulates the starburst, preventing it from consuming all the gas and leaving some remainder even after the most intense phase ends. After the first passage, the galaxies will separate, their relative motion carrying them apart even as gravity works to pull them back together. The separation might last several 100 million years, time enough for the induced star formation to decline somewhat, and for the tidal tails to stretch even farther across space. Then gravity will win, and the galaxies will approach again for a second passage, which will be similar to but less dramatic than the first, because some of the gas has already been consumed, and some orbital energy has been transferred into tidal tails. Additional passages will follow, each one less dramatic than the last, as the galaxies gradually lose orbital energy and spiral toward final merger. Throughout this process, the dark matter halos of the two galaxies will interact and merge. Dark matter, being collisionless, doesn't experience ram pressure or shocks the way gas does. Instead, dark matter particles from each galaxy simply pass through the other galaxy, their orbits altered by gravity, but the particles themselves unaffected. The dark matter halos will interpenetrate during the passages and gradually merge into a single, larger halo through a process called violent relaxation, where the time-varying gravitational potential transfers energy between particles and creates a new equilibrium configuration. The stellar disks will be destroyed during the merger, their organized rotation transformed into the random motions characteristic of elliptical galaxies. This process, called dynamical heating, occurs as stars experience gravitational perturbations from the time-varying potential during the merger. Each star's orbit changes unpredictably, some stars gaining orbital energy and moving to larger radii, while others lose energy and sink toward the center. The net result is a distribution of stellar orbits oriented randomly, rather than concentrated in a thin, rotating disk, creating the three-dimensional, roughly spheroidal shape of an elliptical galaxy. The supermassive black holes at the centers of both galaxies will be drawn toward the center of the merged system by dynamical friction, the process where gravitational interactions with surrounding stars transfer momentum and cause massive objects to sink toward regions of highest stellar density. Initially separated by hundreds of thousands of light years, the black holes will gradually approach each other over hundreds of millions of years. When they reach separations of a few light years, close enough that they become gravitationally bound to each other, they form a binary black hole system that orbits progressively closer as gravitational waves carry away orbital energy. The final coalescence of the black holes, when they merge into a single object, will occur extremely rapidly, the last few orbits completing in seconds or minutes as the black holes spiral together at relativistic speeds before merging in a burst of gravitational waves. This event will be detectable by gravitational wave observatories, like LISA, the planned space-based detector, providing a unique window into the final moments of black hole merger and the properties of spacetime in the extreme gravity near merging black holes. The remnant galaxy will be an elliptical, lacking spiral structure or organized rotation, containing primarily old stellar populations, since most star formation will cease after the gas is consumed or expelled during the starburst. It will be a massive elliptical, one of the largest galaxies in the local group, containing the combined stellar populations of both progenitors plus the new stars formed during the merger. This merged system will slowly evolve afterward, its stellar population aging as no new stars form, its structure gradually changing through stellar evolution as massive stars die and leave behind compact remnants, and through continued minor mergers as it accretes dwarf galaxies from the local group. If humanity, or our descendants, still exist 4.5 billion years from now, when the Milky Way and Andromeda collide, what would they observe from their vantage point within one of the merging galaxies? This question captivates the imagination because it makes the cosmic drama personal, connecting galactic scale events to the human experience of watching the night sky. The answer combines what we know about galaxy mergers with the geometry of how the collision will unfold to paint a picture of a sky transformed over millions of years. Today, Andromeda appears as a faint, fuzzy patch in our autumn sky, visible to the naked eye under dark skies but not particularly prominent, spanning roughly 6 times the apparent diameter of the full moon, though most of that extent is too faint to see without telescopes. As the collision approaches, Andromeda will grow gradually larger and brighter in our sky, though the change will be imperceptible on human timescales, requiring millions of years to become noticeable. 1 million years before the first close passage, Andromeda would appear perhaps twice its current apparent size, noticeably larger to anyone comparing to careful measurements, but still not dramatically different to casual observers. By 100,000 years before first contact, changes would become more obvious. Andromeda would span a significant fraction of the sky, no longer a small fuzzy patch but an extended structure with spiral arms visible to the naked eye under dark skies. The galaxy would appear brighter as well, not because its intrinsic luminosity has increased, but simply because it is closer, its light less diluted by distance. The approach velocity would be measurable over human timescales, the galaxy's apparent size noticeably increasing over decades or centuries. In the final millennia before collision, Andromeda would come to dominate the night sky. The galaxy would stretch across tens of degrees, its spiral structure clearly visible, individual star-forming regions, potentially resolvable as distinct, bright patches. The Milky Way's own structure would still be visible as the band of light across the sky, but Andromeda would provide a second grand structure, a mirror image showing what an external observer sees when looking at a large spiral galaxy. For the first time in human history, assuming humans or their descendants still exist, our species would directly observe galactic structure from outside, seeing clearly what observers in Andromeda would see when looking at the Milky Way. The first passage would bring the most dramatic changes. As the galaxies interpenetrate, tidal forces would begin distorting both structures, pulling out tidal tails and creating bridge features connecting the galaxies. These structures would be visible as long streams of stars and glowing gas stretching across the sky, arcs and filaments that would slowly evolve over thousands or millions of years. The night sky would contain structures at all scales, from individual stars in our local stellar neighborhood to the grand bridges and tails connecting the merging galaxies across the sky. Star formation triggered by the collision would create new stellar associations and clusters throughout both galaxies, including potentially in our local region if by chance gas clouds collide nearby. The rate of supernova explosions would increase significantly as the massive stars formed in the starburst reach the ends of their lives. From Earth or whatever planet our descendants inhabit, this might manifest as supernovae, becoming much more common events, perhaps occurring in our galaxy every few years or even every few months, rather than the current rate of roughly one per century. Some of these supernovae might occur close enough to be spectacularly bright, potentially rivaling Venus or even the full moon in brightness, though close enough to be dangerous, would be extremely unlikely given the vast scale of galaxies. The risk to Earth or the solar system from the collision itself would be minimal despite the violence on galactic scales. The chances of another star passing close enough to perturb the solar system significantly are vanishingly small, given the vast distances between stars. Even during the most chaotic phases of the merger, when stars from both galaxies are interpenetrating and the stellar density is locally enhanced, close approaches would remain rare events. The solar system would likely survive physically intact, though its orbit around the galactic center would be altered, possibly significantly, by the changing gravitational potential. A more subtle but potentially significant risk comes from the supernova rate increase. If a supernova occurs within about 30 light-years of Earth, the radiation and cosmic rays could affect Earth's atmosphere and potentially harm life on the surface. The increased supernova rate during the starburst increases the probability of such close supernovae, though the absolute risk remains low, given the three-dimensional volume involved and the short duration of the starburst compared to geological timescales. Still, it represents one of the few ways the galaxy merger could directly affect conditions on Earth. Over millions of years, as the merger progresses through multiple passages and eventual coalescence, the night sky would transform from a stable configuration we would recognize to something entirely alien. The familiar constellations would slowly distort as our solar system's orbit changes, carrying us to different regions of the merging galaxies. Andromeda would cease to be a discrete object in the sky, instead merging with the Milky Way structure to create a single, complex, evolving system filling large portions of the sky. The eventual elliptical remnant would present a much less structured appearance than either spiral progenitor, lacking the organized disk and spiral arms, instead showing a more uniform distribution of stars in a three-dimensional, football-shaped structure. For civilizations capable of space travel, the collision would present unprecedented opportunities for exploration and study. For the first time, two major galaxies' stellar populations would be accessible within a single system, allowing direct comparison of stars formed in different environments. The ongoing star formation triggered by the collision would provide opportunities to study this process at levels of intensity rare in the modern universe. The merger of the central black holes, if observable through gravitational wave detectors or electromagnetic signatures, would provide unique insights into these exotic objects and the nature of space-time in extreme conditions. As you imagine watching this cosmic transformation from a ringside seat within one of the merging galaxies, consider the mixture of beauty and terror such an event would inspire. The night sky, which has been humanity's constant companion and source of wonder throughout our existence, that would undergo transformation on timescales, long compared to individual human lives but short compared to the age of the universe. A reminder that even the apparently eternal heavens change and evolve over cosmic time. When the dust settles, both literally and figuratively, when the starburst has consumed or expelled most of the gas, when the black holes have merged, and when the stellar populations have settled into their new dynamical equilibrium, what remains will be fundamentally different from either of the galaxies that merged to create it. The spiral structures of both progenitors will be destroyed, replaced by the smooth, three-dimensional distribution of stars characteristic of elliptical galaxies. This remnant, containing the combined stellar population of both Andromeda and the Milky Way, along with stars formed during the merger, will be one of the most massive galaxies in the local group and a dominant gravitational force in our cosmic neighborhood. Elliptical galaxies, like the merger remnant, are fundamentally different from spirals in several key ways. They lack the organized rotation of spiral disks, where all stars orbit in the same direction in a thin plane. Instead, stars in ellipticals follow orbits with random orientations, some orbiting one way and some the other, some in nearly circular paths and others in highly elongated ellipses. This random distribution of orbital shapes and orientations creates the three-dimensional, roughly ellipsoidal shape that gives these galaxies their name. The velocity dispersion, the spread of velocities around the mean, is much higher in ellipticals than in spiral disks, reflecting the random motions rather than ordered rotation. The stellar population of the remnant will be primarily old and red. Most stars currently in Andromeda and the Milky Way are yellow or orange, stars similar to or somewhat cooler than the Sun, and these will continue to shine for billions of years after the merger. The blue stars, hot massive stars that dominate the light from spiral galaxies' arms, have short lifetimes and will die quickly after the starburst ends, fading from view and leaving the galaxy redder. The remnant will contain little gas after the starburst, and galactic winds expel or consume most of it, so star formation will essentially cease, and the galaxy will slowly fade over time as its stellar population ages and the longest-lived stars gradually exhaust their nuclear fuel. The size of the remnant will be substantial. Elliptical galaxies generally occupy larger volumes than spirals of comparable mass, because the random, stellar motions require larger radii to contain the same mass at similar densities. The remnant might extend to 300,000 light-years or more from its center, significantly larger than either Andromeda or the Milky Way individually. This expansion occurs naturally during the merger, as the changing gravitational potential does work on stellar orbits, increasing their energies and expanding the system. The central region of the remnant will be particularly dense, containing stars from the bulges of both progenitor galaxies, plus potentially stars that sink to the center through dynamical friction during the merger. The supermassive black hole, containing the combined mass of both progenitors' black holes, will sit at the dynamical center, marking the point around which the entire system orbits. This central black hole, having merged and settled down after any gravitational wave recoil, will likely remain relatively quiet, accreting gas only slowly, since little gas will remain in the system after the starburst. However, if gas does somehow accumulate near the center, perhaps through the late-time accretion of a gas-rich dwarf galaxy, the black hole could light up temporarily as an active galactic nucleus, outshining the entire rest of the galaxy. Globular clusters from both progenitor galaxies will survive the merger largely intact. These dense stellar systems are small enough and tightly bound enough that they act essentially as single particles during the merger, their internal structures unaffected by the tidal forces that disrupt the galactic disks. The remnant will inherit the globular cluster systems of both progenitors, perhaps 700 or 800 clusters in total, making it a rich elliptical with an extensive globular cluster system. These clusters will orbit through the halo of the remnant, their paths altered by the merger, but the clusters themselves preserved as ancient stellar populations, remembering the galaxies that once existed. The dark matter halo of the remnant will be more massive and more extended than either progenitor's halo, though not simply the sum of both, because some dark matter will be lost during the merger, ejected to large distances by gravitational interactions during the chaotic phases. The halo will retain the roughly spherical or triaxial shape predicted by simulations of dark matter structure formation and it will continue to gravitationally dominate the system, containing perhaps 10 times as much mass as the visible stars and gas. The environment around the remnant will also be affected by the merger. The tidal tails and bridges of stars pulled out during the collision will eventually disperse or fall back onto the merged galaxy, though this process might take billions of years. The intergalactic medium around the remnant will be enriched with heavy elements ejected during the starburst, metals produced by star formation and supernovae, and then expelled in galactic winds. This enrichment will affect any future star formation in the region and will alter the properties of gas that might later accrete onto the remnant or other nearby galaxies. Smaller galaxies in the local group will be affected by the merger as well. Some dwarf galaxies currently orbiting Andromeda or the Milky Way might be disrupted during the collision, their stars stripped away and added to the tidal debris. Others might survive, but have their orbits dramatically altered, potentially being ejected from the local group entirely if gravitational interactions during the chaotic merger phases give them enough velocity to escape. Still others might eventually merge with the remnant, adding their stars and dark matter to the system in minor mergers that will continue for billions of years after the major merger completes. The long-term evolution of the remnant will be relatively quiet compared to the dramatic merger that created it. With little gas remaining and little accretion of new gas expected, star formation will be minimal or absent, and the galaxy will slowly fade as its stellar population ages. The most massive stars will all have died within a few 100 million years after the merger, leaving behind neutron stars and black holes. Sun-like stars will continue shining for billions of years, eventually becoming red giants and then white dwarfs. The lowest mass stars, red dwarfs, will shine for trillions of years, outliving all other stellar types, and eventually becoming the only surviving stars in the galaxy after more than 10 trillion years. The merger of Andromeda and the Milky Way represents in microcosm the fate of many galaxies in the universe. Major mergers are common events in galactic evolution, occurring when two galaxies of comparable mass collide and merge. Many of the elliptical galaxies we observe in the universe today likely formed through major mergers, similar to the Andromeda-Milky Way collision. And by studying these nearby systems and combining observations with simulations, we can understand what will happen in our own cosmic neighborhood and how mergers shape galactic populations throughout the cosmos. As you contemplate this distant future remnant, this elliptical galaxy born from the collision of two spirals, consider how it represents both an ending and a beginning. The spirals we know will be destroyed, their beautiful structures obliterated by gravitational forces. But from this destruction comes a new galaxy with its own character and its own future. The stars that exist today, the Sun included if it still exists, will continue their journeys through space in new orbits within a new galaxy, carrying with them the memory of where they came from and the story of the collision that reshaped their cosmic home. And perhaps, if intelligent observers still exist when this transformation completes, they will look out at a universe that seems familiar yet different, recognizing in the elliptical galaxy that surrounds them the descendant of two great spirals that once danced in the darkness and eventually merged in a union that transformed them both. And so we return, here on Whispering Universes, to where we began. That faint patch of light in the autumn sky, that neighbor in the dark that has accompanied our galaxy since both were young. Andromeda, hanging in the constellation that bears the name of an ancient princess, has revealed itself to be far more than a simple collection of stars. It is a vast system containing 1 trillion suns, each on its own journey through space and time. It is a laboratory where we can study processes difficult to observe in our own galaxy. It is a mirror showing us what observers in other galaxies might see when they turn their instruments toward the Milky Way. And it is, ultimately, our destiny, bound to us by gravity, in a dance that will end only when both galaxies merge into something new. We have traced Andromeda's structure from its spiral arms to its central black hole, from the ancient stars in its halo to the youngest stars forming today in molecular clouds compressed by density waves. We have explored its satellite galaxies and tidal streams, evidence of a violent past where smaller systems were captured and consumed. We have examined the dark matter that provides the invisible scaffolding supporting all the visible structure. We have looked forward to the collision that awaits, the merger that will transform both galaxies and reshape our cosmic neighborhood. What emerges from this exploration is a picture of galaxies not as static structures, but as dynamic, evolving systems shaped by gravity and time. Andromeda has been building itself for 13 billion years through star formation and through mergers with smaller galaxies, and it will continue evolving until its merger with the Milky Way writes a new chapter in its history. The stars we see today, when we look toward Andromeda, are messengers carrying information about the past, about the conditions that prevailed when they formed, about the galaxy's journey through cosmic time. As you drift towards sleep, imagine looking up at that faint patch of light, knowing now what it represents. Those photons entering your eye left Andromeda 2.5 million years ago, traveling across intergalactic space while on Earth. Our ancestors were just beginning to shape tools and walk upright across the African plains. The light shows us the galaxy as it was, frozen in the ancient past, though the galaxy itself has continued evolving in ways we cannot yet see. Changes that occurred in the last 2.5 million years, but whose light has not yet reached us. The universe remains patient, unfolding on timescales that dwarf human experience, but which we can nevertheless observe and understand through careful study and the application of physical law. Andromeda approaches at 110 kilometers per second, a velocity that seems enormous by human standards, but which requires billions of years to cross the gulf of space separating us. The collision, when it comes, will be both violent and beautiful, destructive and creative, ending two galaxies and beginning one. For now, Andromeda remains our quiet neighbor, shining steadily in the autumn sky, a reminder that we live in a universe populated by islands of matter and light, separated by vast reaches of darkness. Among all these islands, Andromeda is our closest large companion, near enough to study in detail, far enough to see as a whole, bound to us by forces that will eventually bring us together. Thank you for joining us on Whispering Universes for this exploration of the Andromeda Galaxy. Sleep peacefully under skies that contain wonders beyond counting, knowing that even the darkness between stars is filled with meaning, and that our cosmic neighbor continues its patient approach across the void, heading toward a future where two galaxies become one.